In section 4, we are going to talk about rational equations. So let's start with a definition. A rational equation is an equation with at least one rational expression. So for example, x over x plus 2 equals 7 is a rational equation. I have one rational expression, x over x plus 2, which is all that's necessary. I could also have something like 1 over x plus 1 plus x over x plus 1 equals 3 over x plus 2, in which case I have three rational expressions. So the only requirement is that you have at least one. So when it comes to solving rational equations, what we want to do is get rid of the fractions, because we don't like to solve equations that have fractions. So the way we're going to do that is we're going to multiply the numerator or numerators, depending on how many rational expressions you have, by the LCD to get rid of the fractions. So once I get rid of the fractions, then it just becomes solving a linear equation, which we have done plenty of times. Now, one thing you have to look out for when you're solving a rational equation is something called an extraneous solution. So an extraneous solution is a solution that makes a denominator equal 0. So you always have to check your solutions with the original equation, because you could get a value for x, but when you plug it back into the original equation, it's going to make at least one of the denominators 0. And if you remember, we cannot divide by 0, which means it doesn't actually work. So you can still get a value for x, but there end up being no solution. So let's take a look at our first example. So we have 5 over x minus 3 equals 12 over 2x plus 3. So in this case, when I'm identifying my LCD, my denominators are already factored, and the only thing that are in my denominators are x minus 3 and 2x plus 3. So we're going to go ahead and multiply our numerators by the entirety of the LCD. So it is a little bit different from adding and subtracting, where we only multiplied by what was missing. In this case, we're going to always multiply by the entirety of the LCD. And the reason we do that is because something is going to cancel. Like in my first fraction, the x minus 3's are going to cancel. And in my second fractions, the 2x plus 3's are going to cancel. So I'm left with 5 times 2x plus 3 equals 12 times x minus 3. And now I have a linear equation. And in order to solve this, I'm going to distribute on both sides. So we get 10x plus 15 equals 12x minus 36. And now I'm going to solve for x. So first I'm going to subtract 10x. So we get 15 equals 2x minus 36. Then we're going to add 36 to both sides. We get 51 equals 2x. Divide by 2, and we're going to get x equals 51 over 2. We are going to leave it as a fraction. We are not going to write decimals here. And I don't really need to check to see if this makes the denominator 0, but just to make sure, so my denominators equal 0 when x is 3 or x is negative 3 over 2. And 51 over 2 is neither of those values, so I don't have to worry about there being an extraneous solution. So our next example, we have 5 over x minus 3x plus 6 over 2x equals 7 over 2. So again, all my denominators are factored. So if I'm looking, my LCD is going to be 2x. So I'm going to multiply all my numerators by 2x. And in my first fraction, the x's are going to cancel. In my second, 2x is going to cancel. And in my third, the 2's are going to cancel. So I have 5 times 2 minus the entirety of what remains, 3x plus 6, equals 7 times x. So 5 times 2 is 10. I'm going to distribute my negative. So minus 3x minus 6 equals 7x. Combining like terms, I get negative 3x plus 4 equals 7x. We're then going to add 3x to both sides. We get 4 equals 10x. Divide by 10, and 4/10 can simplify, so we get that x is 2/5. And in this case, the only thing that can make a denominator 0 is 0, because the only way x equals 0 is if x is 0. And since 2/5 is not 0, there's no extraneous solution. In our third example, we have 3x over 3x minus 1 plus 1 over x equals 1 over 3x minus 1. So again, all of my denominators are factored. So my LCD is going to be x times 3x minus 1. So when I multiply my numerators by my LCD, in my first fraction, the 3x minus 1 is going to cancel. In the second, the x's. And in the third, the 3x minus 1. So we have 3x times x plus 1 times 3x minus 1 equals 1 times x. So 3x times x is 3x squared, then plus 3x minus 1 equals x. Now in this case, I have a squared term. So anytime I have a squared term, I'm going to solve for x by factoring, which means I need to get my equation equal to 0. So we're going to subtract x from both sides, and we end up with 3x squared plus 2x minus 1 equals 0. Now to factor that quadratic, we're going to use our box method. So we have our 3x squared and our negative 1. 3 times negative 1 is negative 3. So I'm looking for the numbers that multiply to negative 3 and add to 2. And there is only one way to multiply to 3, and that's 3 and 1. So it's going to be 3 and negative 1. So we'll have 3x and negative 1x. So when I factor out a GCF from 3x squared and 3x, I get 3x. From negative 1x and negative 1, it's negative 1. 3x squared and negative 1x is just x. And 3x and negative 1 is just positive 1. So I have 3x minus 1 times x plus 1 equals 0. And I'm going to set both of those equal to 0 to solve for x. So 3x minus 1 equals 0, and x plus 1 equals 0. So for my first one, when I solve, I'm going to add 1. So we get 3x equals 1. And then we're going to divide by 3, and we get that x is 1/3. For our second, we're just going to subtract 1, and we get that x equals negative 1. Now in this case, I do have an extraneous solution, because if you go back to our factored form, one of my factors is part of my LCD, the 3x minus 1. So I don't technically have to solve for x. I can know right away that that's going to be an extraneous solution because it's going to make one of my denominators 0. So x equals 1/3 is not a solution. The only solution that's going to work is the x equals negative 1. So it is important that you always check both solutions no matter what. So let's take a look at a couple examples where our denominators are not already in factored form. So we have 2x over x minus 4 plus 10 minus 5x over x squared minus 16 equals x over x plus 4. So the first thing I need to do is factor my x squared minus 16, which factors as x plus 4, x minus 4. And I'm going to tell you right now, 99% of the time, if one of your denominators isn't factored and the other two are, the denominator that isn't factored is going to factor as the other two denominators. I'm not going to give you anything that has a super complicated LCD. So in this case, my LCD is x plus 4, x minus 4. So we multiply our numerators by our LCD. From our first fraction, the x minus 4 is going to cancel. From our second, both of them are going to cancel. And from our third, the x plus 4 is going to cancel. So I'm left with 2x times x plus 4 plus 10 minus 5x equals x times x minus 4. So we distribute in their parentheses. We get 2x squared plus 8x plus 10 minus 5x equals x squared minus 4x. Gonna combine like terms on the left, and we get 2x squared plus 3x plus 10 equals x squared minus 4x. Now, I do have x squareds on both sides of my equation. Unfortunately, one of them is a 2x squared and the other one is just a 1x squared. So they're not going to cancel here, which means I am going to have to factor to solve for x. So I need to get it equal to 0. So I'm going to subtract the x squared and add the 4x to both sides. So we get x squared plus 7x plus 10 equals 0. I do not have to use the box method to solve for x here. I'm just looking for the numbers that multiply to 10 and add to 7, which are 5 and 2. So we'll have x plus 5, x plus 2 equals 0. So we do x plus 5 equals 0 and x plus 2 equals 0. We'll subtract 5, so we get x equals negative 5, and we'll subtract 2, and we get x equals negative 2. Now, when I put my quadratic in factored form, neither of my factors were part of my LCD, which means neither of these values make my denominator 0, which means both of them are solutions. So you can have more than one solution to a rational equation. You're not required to have only one. You could potentially have two. For our last example, we have 2x over x plus 4 plus 7x plus 12 over x squared plus 6x plus 8 equals x plus 1 over x plus 2. So when I factor x squared plus 6x plus 8, it is going to factor as x plus 4 times x plus 2. So that tells me my LCD is x plus 4, x plus 2. So I'm going to go ahead and multiply my numerators by my LCD. In the first fraction, x plus 4s are going to cancel. In the second, everything will cancel. And in our third, the x plus 2s will cancel. So that leaves us with 2x times x plus 2 plus 7x plus 12 equals x plus 1 times x plus 4. Now notice here that on the right side, I put the x plus 1 in parentheses because I'm going to have to distribute. Everything in x plus 1 has to multiply to everything in the x plus 4. So when I distribute on the left, I get 2x squared plus 4x plus the 7x plus 12 And when I distribute on the right, I'll get x squared plus 4x plus x plus 4. So this time I have to combine like terms on both sides. So on the left, I get 2x squared plus 11x plus 12. And on the right, I'm going to get x squared plus 5x plus 4. Now, similarly to the last example, my x squareds aren't going to cancel, so I'm going to have to move everything over. So I'm going to subtract x squared, 5x, and 4 from both sides. And we're left with x squared plus 6x plus 8 equals 0. So when I factor that, I end up with x plus 4, x plus 2 equals 0. And one thing I could notice straight away is x plus 2 times x plus 4 is my LCD, which means I'm definitely going to have values that make my denominator 0. So I don't even have to solve for x because I know neither of these solutions are going to work because at least one denominator is going to be equal to 0. So when both of them end up canceling, the answer is no solution. So unfortunately, you could go through all of that work to identify your LCD and cancel and solve for x and have your solution be extraneous and there be no answer, which is going to happen. So let me know if you have any questions on how to solve a rational equation or what an extraneous solution is.